Since the Industrial Revolution, human reliance on fossil fuels have altered the basic chemical composition of the atmosphere, causing the entire planet to warm. We have pushed the CO2 content of the atmosphere from around 280 parts per million in pre-industrial times to well over 400 parts per million according to the latest measurements. The average global surface temperature is about 1 degree Celsius higher than it was before the Industrial Revolution. A warmer climate means more and more powerful extreme weather events, ecological collapse, diminishing agricultural production, rising sea levels, and so on. The warmer it gets, the worse the consequences. To avoid the worst consequences, we have to cut back emissions and probably remove CO2 from the atmosphere. But how much and when? Some economists have tackled this problem by weighing mitigation costs against the cost expected to come with warming itself in order to try to find some balance between the two. Too much mitigation, they argue, and the costs may outweigh the benefits and will tank the economy for no good reason. Too little mitigation, and climate disaster tanks the economy for us. Somewhere between the skill of under-mitigation and Charybdis of over-mitigation is a golden balance, or so the thinking goes. Conducting such an analysis is typically done by deploying so-called integrated assessment models, or IAMs for short. These models integrate economic and climate modules in order to balance benefits and costs for various policy pathways, and they have in recent decades become increasingly important in studying the impacts of climate change and exploring the effectiveness and viability of various mitigation pathways. Studies based on these kinds of models feature heavily in the reports of the IPCC. They're a central tool in constructing the emission scenarios that drive large-scale climate modeling exercise, such as the coupled model intercomparison project. And as a testament to their importance, the 2018 Sveriges Riksbank Prize in Economic Services in memory of Alfred Nobel was awarded to the economist William Nordhaus for his development of the Dynamic Integrated Climate Economy Model, or DICE for short. But the models have been relentlessly controversial and the subject of considerable debate. One reason is the often worryingly high temperature increases that the models sometimes prescribe as optimal. For example, according to the aforementioned DICE model, we should aim for a global average surface temperature of just north of 3 degrees Celsius in year 2100, with even higher temperatures thereafter. For many, especially climate scientists perhaps, this seems like too much. Even a 2-degree world is fraught with danger. Another reason for controversy is the way the models appear to provide a rationale for delaying action on climate change. Assumed baseline economic growth and the discounting of long-term effects of climate change seem to always make waiting until tomorrow the preferred approach. Contrary to this, defenders of the models argue that they're useful tools that in a transparent, sometimes quick and often rigorous way can be used to explore and compare the many policy options that lay before us. In this lecture, I will focus on two sets of disagreements with respect to the usefulness of IAMs in climate impact and mitigation research and policy. I will try to show how what seems like a simple disagreement on the value of some parameter or the functional form of some particular component are underpinned by much more fundamental philosophical issues concerning the nature of the science itself, its core values, and role in society. The focus will be on two cases. The first concerns what is called inter-temporal discounting. That is, how we are to compare the well-being or utility of future generations with that of our own. This is a long-standing issue in welfare economics, but has been a central debate in the context of climate change recently, especially following the publication of the so-called Stern Review about 15 years ago. The other concerns the damage function. So the damage function is a function in an IM that assigns to a given temperature rise a certain cost. Now, before we proceed into the cases themselves, we have to say something about what an IAM is. As a group of models, they're a motley bunch. They're all modular in some sense of the word. They couple representations of various interconnected subsystems, but they can otherwise be quite different from one another. Some are enormously complex constructions with countless submodels that on their own have a high degree of complexity. Others are simple and can be exhaustively described by only a handful of equations. The kind we will be examining here are primarily optimization models. They're typically towards the simpler end of the spectrum. So although the degree of detail varies a great deal, even from within this subcategory of models, the basic structure is roughly as follows. So economic growth, population growth, and carbon intensity, those kinds of things are often exogenous to the model. So these are essentially assumptions that are fed into the economic growth model that generates gross economic output. Via an abatement function, emissions are calculated as a function of abatement together with gross economic output. So there you have net emissions. The climate model inputs emissions and outputs temperature rise, from which damages are calculated via the damage function that are then fed back into the economic model. On top of this is an optimization structure, the objective function. This is a social welfare function that sums discounted welfare over time. That is to say, it expresses future costs and benefits in terms that apply to the present. These kinds of models output a wide range of parameters, the most important of which is probably the so-called social cost of carbon. The social cost of carbon is the present social value of 1 extra ton of carbon emitted into the atmosphere. This parameter can then be, in the best of worlds anyway, used to set, for example, optimal carbon taxes. So this graph that you see here shows the DICE model run with the default settings. A good place to start with the discounting debate is the Stern Review, or the Economics of Climate Change, as the report's full title read. So this is Nicholas Stern, or Sir Nicholas Stern. The report was commissioned in 2005 by the British Chancellor of the Exchequer, it was Gordon Brown at the time. The purpose was to investigate the economic implications of climate change and what viable routes of action there were for the UK. Upon its publication, the report was immediately a source of considerable controversy with its dire forebodings and high prescribed mitigation costs. The report suggests that the economic impact of failing to act on climate change would be at least 5% of GDP for the UK then, each year, now and forever, Stern writes, and could be as much as 20% if a wider range of risks and impacts are taken into account. Stern projected climate damages that far outstrip what many other economists had estimated, and stood out among his peers in advocating for a much more ambitious set of climate policies. Now, the critics didn't wait around. There are countless papers discussing the report and its flaws, and one central concern raised among Stern's many critics was his unusually low intertemporal discount rates. Now, when utility is compared across time, there are actually several discount rates that come into play. So this is perhaps best illustrated by looking at a so-called Ramsey optimal growth model. So this is an important component in many IAMs. In this equation, the R is the consumption discount rate, rho is the utility discount rate, or pure rate of time preference. We're here going to refer to this as the PRTP. Eta is the elasticity of marginal utility, and G indicates growth. As mentioned before, growth is usually exogenous in these kinds of models and assumed to be around 2% or so for the coming century. Now, the elasticity of marginal utility, or interpersonal inequality aversion, that is eta in the equation, reflects the intuition that $1 in the hands of a poor person has more utility than $1 in the hands of a rich person. This kind of discounting has a temporal dimension insofar as per capita wealth is different across generations. If future generations are richer than the present one, it doesn't make any sense to make a lot of sacrifices now in order to make them even better off. Notably, this is not a discount on well-being or utility, but on some monetary unit. The point is not that the well-being of rich people should be discounted per se. It's not that their well-being is worth less than the well-being of poor people, but that if you are rich, you get less utility out of a dollar more compared to someone who is poor. So this kind of situation arises, that is the temporal discounting of this kind of discount rate, if the economy grows faster than the population, which is typically assumed to happen. The PRTP, on the other hand, works differently. This is indeed a discount on well-being and not on money. It discounts the well-being of future generations not because they're richer than the present one, but simply because they're in the future, just as it discounts one's own future well-being. A positive PRTP reflects a preference for well-being in the present, with a positive rate making some sacrifice in well-being in the present, for example by cutting back on consumption of something, will only make sense if this means that there is going to be even more well-being in the future. With a PRTP that's zero, one is indifferent to well-being now and in the future, and a negative rate means a preference for well-being that is in the future, so one is willing to make an overall sacrifice to have some well-being in the future. Now, conventional estimates of G, rho, and eta tend to be around 2% for each, ending up with a consumption discount rate of 6%. Stern stands out among his peers in having a very low estimates of all three, but in particular the PRTP. Instead of using 2% or 1.5% or 3% as others have assumed, Stern uses a PRTP of only 0.1%. In the context of climate change, what is at stake is of course diverting resources now towards mitigation, that is making some sacrifices in the present in order to avoid some damages in the future. So all else being equal, a positive and high PRTP means that mitigation efforts now are going to have to avoid a lot of damage in the future for it to make sense to us to commit to them. With a low PRTP, mitigation costs and damage costs become more on par with one another. So it's a very meaningful difference. Even seemingly slight changes in discounts rate can have a lot of impact over 50 or 100 years, especially when combined with other uncertain parameters such as climate sensitivity and climate change damages. The effect on estimates of the SEC become enormous. Ackerman and Stanton, for instance, they use the DICE model but make other reasonable assumptions regarding these parameters, end up with an SEC in 2010 not of around $20 or $21 as Nordhaus does, but rather $900. So Stern's critics immediately picked up on this and wondered why Stern would deviate from the norm on setting the value of parameters of such enormous consequence. So why did he end up with such a low PRTP? Well, the reason for Stern's low discount rates have been fairly clear from the beginning. Stern perceives of the problem of intertemporal discounting largely as a matter of ethics or moral philosophy. The relevant question is it ethically defensible to discount future generations? To see the discounting problem as a philosophical problem is to see it as amenable to philosophical approaches, maybe even solutions. That is to say, there's going to be more a priori reasoning and less observing and measuring. I mean, an important reason for adopting such an approach is, of course, what philosophers like to call the naturalistic fallacy. So how things ought to be should not follow from how things are. So here is Stern on this. He writes, "It is, of course, possible that people actually do place less value on the welfare of future generations simply on the grounds that they are more distant in time, but it's hard to see any ethical justification for this." Stern's conclusion is thus that the PRTP should be 0%. That it eventually ends up being 0.1% has to do with a small but not negligible risk that there will be some disaster, a comet or something, so that there will be no future people to take into account. This way of looking at discounting is called the prescriptive approach, and it is a view that Stern unsurprisingly shares with many philosophers, for instance, who are interested in these kinds of issues. Among economists, this is a minority view, as Stern critics often point out. If Stern's prescriptivist philosophizing is the minority view, then what's the majority view? Well, it is what Arrow and colleagues call the descriptivist approach, or the descriptivist view. This approach to the PRTP perceives of it as subject to measurement, an uncertain empirical quality like any other. Establishing the appropriate discount rate is indeed a matter of measurement and observation, and it should be in line with the kinds of behaviors that we can see and observe in the real world, such as, for example, in financial markets. Arrow and colleagues, when they try to flesh out this view, they write that the descriptivist believes that no justification exists for choosing a social welfare function different from what decision makers actually use. Advocates of the descriptive approach generally call for inferring the social discount rate from current rates of return and growth rates. So contrary to prescriptivists, descriptivists believe that how people actually discount the future is not only relevant, but it's really what we should rely on. This has led the descriptivists to adopt generally much higher discount rates. So the two approaches involve structuring the problem in different ways and thus making different ways of dealing with it appear appropriate, or that's one way of seeing things. How are these approaches justified? Here the prescriptive approach probably seems more immediately intuitive to most people. So what about the descriptive approach? What's the reasoning? So here is a representative remark by Weizmann on Stern. So he writes that Stern is relying mostly on a priori philosopher-king ethical judgments about the immorality of treating future generations differently from the current generation, instead of trying to back out what possibly more representative members of society than Stern himself might be revealing from their behavior is their implicit rate of pure time preference. An enormously important part of the discipline of economics is supposed to be that economists understand the difference between their own personal preferences for apples over oranges and the preferences of others for apples over oranges. So although he admits that establishing the PRTP then is perhaps no trifling task, he continues to write that at least it's a good faith effort at such an inference might have gone some way towards convincing the public that the economists doing the studies are not drawing conclusions primarily from imposing their own values. On this last point, similar sentiments can be traced in Thorén Johei's critique of Stern, where they too worry about what they see as activism on Stern's part, and what this means for the presumably the standing of economics as a science and the already polarized climate debate. So there's clearly a lot going on in these remarks. So first, there seems to be a worry on the part of the descriptivists about economics as a science, its core epistemic values, and how to best live up to those values. There's a strong emphasis on some kind of objectivity. The inquirer should not let her own values and preferences color her reasoning. They're hence suspicious of the prescriptivist's approach on this precise ground. Prescriptivists, from the perspective of the descriptivist, appears to do precisely this, to impose her own value judgments on her subjects. In order to maintain a appropriate value-neutral stance, the descriptivist suggests one should then commit to some objective measure. you kind of get the feeling that any measure will do. Here, of course, the prescriptivists like to point out that since there are many ways of measuring things like preferences that yield different results, what precise measurements you commit to is a decision with considerable ethical implications. A second aspect of Weizmann's remark has a certain moral dimension to it. That is to say, there's something about imposing one's values and preferences on others that go beyond just merely trying to uphold objectivity in science. So this is what Baum refers to as the pro-populist and anti-elitist sentiments among descriptivists. So descriptivists thus often claim that it's democratic to determine discount rates on the basis of people's behaviors as they go about their daily lives. Here, prescriptivists press on the fact that seemingly important constituency, namely the future people whose well-being we're discounting, never get their say. So Baum puts this as follows. He sees this as a difference between these two positions with respect to who they consider to have standing. So for the descriptivist, it is current individuals, strictly speaking, that are active in financial markets. And for the prescriptivists, at least according to themselves, it is current plus future individuals. Finally, there's a kind of pragmatic or practical dimension involved that places science as a means to an end, where that end is a rapid, or at least more rapid, shift towards more ambitious climate policies. That such policies are direly needed is almost universally agreed upon. Less so how the science should attach itself to society in order to best serve those ends. Descriptivists worry about science being perceived of as an activist endeavor and not trustworthy, and that this would in turn have undesirable consequences on policymaking downstream. A conceivable counterposition to this draws on arguments from inductive risk. Scientists should consider broader social risks in setting epistemic standards when those risks are severe and uncertainties are pervasive. Given the consequences of climate change, it seems better to accidentally mitigate too much than mitigate too little. So let's move to the second case. The damage function in an integrated assessment model takes some climate change variables such as temperature and outputs a cost for damages. So there are many different ways of estimating the damages of climate change. Some recent contributions to the field involve on their own sophisticated use of complex models. Often enough, however, the function is fairly simple. Many damage functions conform to the following general form, where dt is the damages, a is some coefficient, t is the difference in warming, and b is some exponent. So in the dice damage function, b is equals 2, so the exponent is 2, it's a quadratic function. The coefficient that Nordhaus uses has been subject to successive changes. The latest version uses the coefficient 0.00227. So this corresponds to damages of 0.227% of GWP at 1 degree Celsius of warming before discounting. So if we plot this over a range of temperature increases from, say, 0 to 10 degrees, we get a curve like the following. 3 degrees of warming gets you about a 2% loss of GWP, and 6 degrees somewhere around 8%, 10 degrees about a 23% loss. Clearly, a different functional form or different choices of coefficients or exponents will yield very different results. Now, there have been a lot of concerns raised about these kinds of damage functions. Here I'm going to limit myself to one issue in particular. So one challenge here is that there is just not enough data to fit the curves to with any degree of confidence. As Petsy notes, the maximum year-to-year change in global mean surface temperature from the 1950s to 2010 was only 0.3 degrees Celsius, and goes on to ask, so how can any modeling based on the last 60 years or so of data derive confidence interval for a global centennial, that is over 100 years, damage from over 3 degrees Celsius of sustained global warming, and hence improve on SCCs that inform emission abatement policies on behalf of distant generations. So what to do? So there are many ways of going about this, but here are two approaches that economists sometimes use. So one is to look at weather and then extrapolate to climate. So the idea here is that you examine the impacts of much greater changes in temperature, precipitation, etc., observed over much smaller time and space scales, and then commit to an assumption that requires that the effect of a marginal change in the distribution of weather is the same as the effect of an analogous marginal change in the climate. Another is to look at spatial differences and then map these onto temporal differences. So one can examine differences in the GDP and average temperature in different places. Often they do this in different places in the US, like North Dakota and Florida, and then assume that spatial relationships also hold over time. So each of these assumptions can and have been called into question, of course. As Steve Keen pointed out in a recent talk at the OECD, as climate change progresses, we're charging the atmosphere and the oceans with energy. This tends to put the system in a qualitatively different state. Correlations of GDP and average temperature differences between different locations says nothing about what happens to the system as its fundamentals are altered, especially not as we push the climate system into extremes with average temperature increases of 3, 4, 5, or 6 degrees Celsius. To conclude, I have in this presentation tried to show how disputes with respect to discount rates and damage functions in IAMs are really underpinned by more fundamental philosophical differences. These include differing methodological assumptions, conceptions of objectivity, how to deal with non-epistemic values in science, and assumptions about how science is influencing policy making. These different assumptions together form an intricate web of interconnected and interdependent ideas, where it's hard to tell what's more fundamental or what's more important to those involved. Both the discounting and damage function issues is a serious threat to the viability of using IAMs for optimization at all. Without a damage function, there is no optimization to be had, period. Thus, other lines of conflict reveal themselves. Where proponents of optimization IAM see technical difficulties, for instance, in getting the right damage function, critics see a fundamentally flawed approach that had better be scrapped altogether. Pindick, for instance, argues that a better way is just to ask experts, economists, that is, what they think. The models, he says, merely serve to obscure, and it would be more transparent if economists would just discuss their assumptions directly instead of burying them in obtuse mathematical structures. Petsy is more optimistic, but calls for a different kind of model put towards different ends. We should be looking for low-cost pathways towards achieving clearly stated aims, rather than searching for centennial optima. That being said, I will end this lecture now, and I want to say thank you.